Okay, ladies and gentlemen, let's get started with the rest of the morning session. We have two speakers in this half, Sunil Mukhi from ISAR Pune and Anindra Sinha from Indian Institute of Science, Bangalore. So first, let me invite Professor Sunil Mukhi, who will talk to us about string theory, elephant in the room of conditioned viewpoints. So Professor Mukhi, I think the organizers would like to greet you with a short. Thank you, the floor is yours.
Okay. Thank you. Okay, thank you for the kind invitation. I especially like to wish Vikash a happy birthday, and it's a wonderful event and I'm really happy to be here. I must start by apologizing for my slightly flaky title and abstract. It was done in a spirit of jest. I'm not very much of an expert on Jain literature, but I like this picture very much. It's seven blind. Oops. Yeah, it's seven blind men seeing an elephant from different viewpoints. And what I've done with this talk is to try and make a essentially non-technical review of a subject that everyone hears about. I hope you find it interesting. My contribution to this is, I won't be talking about my own research, which is quite mathematical and might be boring for people, but what I hope you find interesting is a little bit of a little tool of analysis which I tried to introduce into how we think about theories and whether they are scientific or not. So anyway, since there is a P in the title of this conference and it stands for philosophy, so this is my quote from the Syadavada Manjari of Acharya Malisena. It is impossible to properly understand an entity consisting of infinite properties without the method of modal description consisting of all viewpoints on the maxim of the blind men and the elephant. So I'm going to try my hand at a modal description of string theory. I have no idea what that means, but I'm quite sure that string theory consists of infinite properties, so it is definitely described by this quote. So my talk is divided in four parts. In the first part, I'll try to present my thoughts about different things that in physics we call theories, and I've tried to sort them out into three bins, if you like, called goals, models, and frameworks. And I'm hopeful that in this way, I might contribute a little bit to resolving some of the confusions that people who work in string theory and also who do not seem to get into. Then I'll review some history of the origins and goals of string theory. Then I'll focus on what I think are some important insights, including recent insights. And then I'll talk about these conditioned viewpoints or conditioned perceptions at the end. And Vikash instructed me specifically to be controversial and critical of the string community, and I'll do that at the end. So actually this is an opinion piece I published in Current Science in 2015. No one has read it as yet except me, but I tried to explain my thoughts about this subject, goals, models, and frameworks, and I'll shamelessly sell you those thoughts right now. So, excuse me if I'm very elementary, there are some students here, so I hope at least it will be good for them. So all of us here are familiar with quantum fields, and there are basically three quantum fields that we are happy to live with: the scalar, the fermion, and the vector. But of course, none of them is tied to any specific particle in nature. A scalar can be a pion, it can be a Higgs boson, it can be a glue ball. A fermion can be a quark, or a lepton, or even a proton, or a neutron. And a vector can be a photon, or W boson, or gluon. It can also be a rho meson. And there's more. That was just particle physics. But the same fields, phi, psi, and mu, can describe quasi-particles or collective excitations in condensed matter systems, and there's a rich set of names like phonons, magnons, plasmons, and so on. And the fact that the same formalism can apply in different kinds of systems means that the formalism is really a framework. Quantum field theory, as we know it, is a framework. It's not a model, it's not a theory. It shouldn't be called quantum field theory. It should be called quantum field framework, but it's too late to do that now. Now, to use any framework, we must make a model, and so I'll give some examples. And a model is a concrete proposal to describe a physical system in terms of a given framework. So you need the framework, and then you have to make a model. Now, the only test for a framework is whether it leads to useful models. If it fails to do so, we abandon it. Usually that doesn't happen suddenly, that happens gradually. But in any case, a framework is not falsifiable. There's no experiment you can do which will falsify a framework, because a framework is a framework, it's not a model. Now let's look at a model. The model that everyone knows best within quantum field theory is quantum electrodynamics. And let's note some features of it. It's an excellent model for electrons. It's a fairly decent model to describe protons, only at low energies. As soon as you go to high energies, you start to see proton substructure and the model starts to fail. And it's a useless model to describe neutrinos because they don't couple to photons. So the same model can have different degrees of success depending on where we apply it. Now, let's look at the most excellent application, the one where it applies to electrons. Even there, QED is incomplete, because if you calculate the E plus E minus scattering amplitude in QED, it will at some point disagree with the experiment since it doesn't have the Z contribution. Now, we don't normally conclude that QED is falsified, although this is a popular word. What we do instead is to say it's part of a bigger model, the standard model. But of course, no one expects the standard model to predict all experiments correctly forever. In fact, all known models have a domain of validity. The standard model has probably outdone what was expected of it in terms of domain of validity. So it's a lovely model, but it's still a model, and there are things which will contradict it. Even the very existence of dark matter says there's something in the universe that isn't in the standard model. And that's just how models are. So instead of invoking questions about whether models are falsifiable or not, it's a better approach is to ask how predictive a model is. And once it has predictions, then of course you can test those. What I want to emphasize here is that if it fails those tests, you don't usually throw away the model. You either tweak it or you decide that it doesn't apply. There are such things also in condensed matter physics like Fermi liquid theory, where it fails. For example, you say the system is not a Fermi liquid, it's something else, it's a non-Fermi liquid. That's actually considered an interesting thing. You don't say Fermi liquid theory is falsified. So this is at least my outlook. You can disagree and please say so in the questions later. But I think predictivity is very important, and what it means is that we get more information out than we put in. This is important because there are models used in physics which have so much information put into them that you cannot be really, that you might not be very impressed by what comes out. I mean, after all, if you want to predict a few experimental results, you can always make a model with enough parameters that will fit any curve you like. So predictive there must be a profit in predictivity. It must give you more than you actually put in from the beginning. Okay. So I've talked about frameworks and I've talked about models, but both of them are a means to a goal. And a goal is a specification of what system we would like to understand and what degree of understanding would satisfy us, which can of course change with time. So from this point of view, there are only two considerations in evaluating scientific research. One is whether the goal is valid or acceptable. The second is whether the framework leads to a model which is useful in achieving the goal. Okay. And the standard model is fantastic on both counts. We all agree that the goal of particle physics is valid or acceptable. By the way, there are physicists who don't agree with that, but they're not in this room probably. but many of them have, famously been part of the story. But the standard model is certainly excellent on these counts. Now, with this out of the way, so this is goals, models, and frameworks. Framework is the overarching structure, model is the specific thing you use to predict, and the goal is what you actually want to learn from the system, about the system. Now I'll briefly review some historic facts about string theory, very well known, but still may not be bad to review them in the light of goals, models, and frameworks. So in the 1950s and 60s, with the existence of new accelerators, very low energy by modern standards, but still new, dozens of strongly interacting particles were discovered, and experimenters measured their masses and spins, J, masses M, and found a curious relationship that J seemed to be proportional to M squared. And so if you plot J versus M squared, you find straight lines called Regge trajectories. And here's a nice figure which shows you a whole bunch of Regge trajectories, all of which, interestingly, have the same slope. So the question arose, why are there so many hadrons? Why do they lie on Regge trajectories? Are they made up of something else? And for a while that remained a mystery, but it was in the 1960s, a fabulous time for experiments, and deep inelastic scattering experiments, which also made a, sorry, no, am I not on the, oops. Okay. Oh dear. Okay, well, I think the online audience missed a part of it. I'm sorry, it's not in my control. So deep inelastic scattering already made an appearance in the first talk today, and obviously it's one of the most spectacular experiments in history of the subject. And it showed that these hadrons that we were finding were made up of point-like particles called quarks. But there was still a puzzle. The quarks seemed to be almost non-interacting inside hadrons, and yet they could not be liberated from them, from the meson or baryon, as the case may be. And so there were three weird observations to be reconciled. One was linear Regge trajectories, one was the existence of weakly interacting quarks, and the third was the non-existence of isolated quarks. And one of the approaches used to explain these observations was a model due to Susskind and Nambu, which eventually took a while. It was phrased in language of infinitely many oscillators. It was supposed to explain Veneziano amplitude, so there's a large part of history that I cannot go into here. But the end point of it at the time was this rubber band or string model, which basically ended up modeling, for example, a meson as a string with a quark and anti-quark pair at its ends. Now here's something that really surprised me. I don't know how many of you know it, but these are some words from Dirac's Bombay Lectures 1955. We may regard classically an electron as the end of a single Faraday line of force. The electric field in this picture forms discrete Faraday lines of force which are to be treated as physical things like strings. One has then to develop a dynamics for such a string-like structure and quantize it. Now, it seems to me that Dirac was actually wrong, because the electromagnetic field has force lines that spread out and they don't behave much like strings at all. But the chromomagnetic field, the color field on the contrary, has collimated flux lines, and it's a very good candidate to describe by quantizing a string-like structure. And in fact, it's quite easy to show that a quantized relativistic string has excitations satisfying this linear relation between J and M, where the coefficient of M squared, J and M squared, where the coefficient is 1 over 2 pi times the tension in the string. And the fact that the tension is constant is the statement that this is a linear trajectory. So the nice thing is it explained the observed Regge trajectories. It also explained the weakness of inter-quark forces at short distances, because if it's like a string, a rubber band, then at short distances it becomes slack effectively, or you could say there's not much energy in that rubber band because the total energy is its length times its tension. But on the other hand, if you try to pull quarks apart, you get a linearly growing potential and that keeps the quarks connected, or as we say today, confined. These are all approximate statements, but they're pretty useful at the time when this kind of dynamics had not previously been thought of. However, as everyone here knows, once quarks were understood through QCD and through the Engel's force, then that view started to dominate. And well, people accepted the idea that maybe strings are one description of the system and gluons are another description of the same system, maybe valid in different domains. Particularly gluons work very well at short distances, and maybe the string is a better description at long distances. Now the string could be derivable from QCD in principle, but maybe not in practice. Just like in condensed matter systems, we have quasi-particles or collective excitations, but we don't really claim these are new objects in a condensed matter system. They must come from the atoms and the electrons and nuclei and nothing else in principle, but in practice it's not very easy to derive it, and so instead you assume it. So it's a similar sort of idea. Okay, so that's what was called the QCD string, and what's now called the QCD string. And this is an open string, but the same theory also has closed strings. Now, a very important theoretical development in the 1970s showed that if you quantize an open or closed string, of course, as you would expect from any string, you get a spectrum of excited states. What was surprising is that because of some subtle field theoretic properties of this string worldsheet theory, the lowest excitation is massless and has spin 1 for open strings and spin 2 for closed strings. Now technically it's not the lowest excitation even though it's massless, unfortunately, and as I've shown here, what happens is that there's actually an excitation below the massless one, which means its mass squared is negative. That's called a tachyon. Now Nambu's original paper had this interesting comment. He said the use of finite dimensional Lorentz tensors, as in the factorized dual model, this is the Veneziano amplitude that he was trying to explain, involves negative probabilities, whereas infinite dimensional unitary representations in general lead to tachyons. So there are two problems: negative probabilities, which he called ghosts, and negative mass squared states, which he called tachyons. So these were, which are normally called tachyons. So these were two inconsistencies of this string approach, and they threatened to destroy the entire structure. But of course, Nambu has some very entertaining comments in his paper, which you should read, which says maybe we should like ghosts and learn to live with ghosts, and maybe ghosts are real. The question is whether ghosts are real. But anyway, far be it from me to comment on Nambu's thoughts, but people reacted to this at the time by asking whether they can find a version of string theory that doesn't have ghosts and doesn't have tachyons. And this was found under two assumptions. One was that the worldsheet degrees of freedom of the string should be rendered supersymmetric. This is not the statement that the string is part of a supersymmetric field theory in space-time, but just that the worldsheet description needs something besides the string coordinate, something fermionic. And the second was that they propagate in 10 rather than 4 space-time dimensions. Now it turns out that the first removes, the supersymmetry removes tachyons, and the 10 dimensions removes ghosts. So in that sense, Nambu's two objections got answered by this step, but it was a very big step. Now, having found this, it was not necessarily obvious what it was good for, but there was another thing that was found, and I put some green stars here. These are things, I think I might have had one here also. The green stars are things I'll come back to later on when I talk about the framework of string theory. So in this same period, it was found that if you make string loop diagrams, then unlike Feynman diagrams in quantum field theory, these are finite in the ultraviolet. Let me announce right away that these stars mean that the property I'm talking about is a framework property, not a property of any particular model, but rather a property of essentially all models within the framework. So it's a property of the string framework. So is this one, that you have these massless spin 1 and spin 2 excitations. And another thing that was found at the same time was that interactions of the massless spin 2 particles build up the interactions of Einstein gravity, the multi-graviton interactions of Einstein gravity, while the massless spin 1 particles build up the interactions of Yang-Mills theory. And it's literally true that if we did not have Einstein's gravity Lagrangian and we did not have Yang and Mills's Lagrangian, then this procedure, which is completely different, would actually allow us to systematically build it up order by order. It would be easy to do for Yang-Mills because Yang-Mills has only 3 and 4 point vertices. It would be difficult for gravity, which has infinitely many graviton self-couplings, but in principle it could be done. And at this point, it became natural to propose that superstring theory, which is the string with the fermionic worldsheet and in 10 dimensions, is a framework for quantum gravity and gauge interactions. So this became a kind of new idea and in fact a new goal. Now, let me just continue with a bit of history and then I'll step back and look at these goals. In 1984, it was realized that the only allowed Yang-Mills gauge groups in the 10-dimensional superstring are E8 cross E8 and SO32. This was quite exciting because in quantum field theory, we can put any gauge group we like. We can write the standard model with SU 2079 if you like. It's not interesting maybe, or maybe it is, but there's no restriction, there's no limitation on what gauge group you can have. But in 10 dimensions, due to anomalies, there's a restriction, and this is the restriction. Note that the groups are fairly small, but they're not too small, and they certainly do include the standard model gauge group and also the other gauge groups people thought of previously for grand unification like SO10, SU5, SO10, SO16, whatever you like, E6. Okay, but that was all very well, that was all 10-dimensional, and as it turns out, it's really a 10-dimensional feature. So the question was, what use is all that to make a model in 4 dimensions? By now the motivation was slowly becoming clear that we want a string model of the gravitational force in 4 dimensions where quantum corrections are computable. Now the point as we understand it today is that the space-time dimension does not really have to be 10. What has to be 10 is a quantity called the superconformal anomaly of the worldsheet theory. This is a consistency which helps the theory get rid of ghosts and tachyons. But that number 10 is D only if we assume a simple flat background. But we can also assume a background with some internal degrees of freedom which have this an anomaly equal to some number C int for internal. And there's no problem in choosing C int to be 6, in which case D can be 4. Now one way to achieve C int equals 6, and I emphasize it's not the only way, is to assume the 10-dimensional space-time is of a product form where there's a 3 plus 1 dimensional space-time identified with the real world, and there's a 6-dimensional internal space